Hey, greetings and welcome, friends. We are starting a new chapter today, and we are going to be talking about triangles, everybody's favorite shape. Man, it's like being in, I don't know, preschool all over again. So first of all, we need to know names of things, because that's what geometricians do. We define things with clarity, we give it a name, and then we discover all sorts of properties about it based on the restrictions we've given it, and then and then expand our knowledge about the universe as a result. So it says the following: classifying triangles by sides. That if there are no congruent sides in a triangle, it is said to be scalene. That if there are at least two congruent sides in a triangle, that is isosceles. Isosceles, and that word can also then be applied to like isosceles trapezoids later on. If you have two congruent sides on a trapezoid. And if you have three congruent sides, it's called equilateral, which you can kind of see equal there and like laterals, sides or something. So there you go. Great stuff. We're learning already. You can name triangles by sides, and you can also identify them or categorize them based on their angles. So if all of the angles are acute or less than 190, wow, then it's an acute triangle. If there is one right angle, it's a right triangle. Is it possible to have two right angles in a triangle? Right, if I have two right angles in a triangle, I know that by the transversal perpendicular lines theorem, that these two sides would then be parallel, and like I couldn't like get them to like warp around to like make a triangle at some point, right? You would just have two parallel sides, and it's not a polygon anymore. Let's see. An obtuse triangle has one obtuse angle, and similar to a right triangle, there can only be one. And an equiangular triangle has three congruent angles. And actually, yeah, it turns out these are the same triangle. True story. True story. Is it possible to have an obtuse isosceles triangle? Yeah, I could have one like that's just kind of like the obtuse would have to be between the two congruent sides. You could have a right isosceles triangle. That's actually going to be a 45, 45, 90 triangle that we'd talk about later. Yeah, and good stuff, good stuff. Anyways, so that's how you can classify triangles by two things. And it says, hey, look at this. What if you're looking at a beam or something? And then you're like, oh, wow, looks like these two are congruent. Let's classify this. So classify it by sides and by measuring its angles. Measuring its angles? Oh dear, I did not plan on doing that. But yeah, how about side lengths here? It's isosceles. Isosceles, right? And this looks less than 90, this looks less than, I'm guessing acute. And if you guys used your protractors, you would find that the angles are 55, 55, and 70, is at least what the book is telling me. And I don't believe that I had deformed the image in any capacity when I've presented it to you. Here's example 2. You can also classify triangles the least fun way, on the coordinate plane, using things like Mr. Waddy's most expertise formula. That sentence was also good. The distance formula. Man. So it says classify by its sides, then determine whether or not it's a right triangle. So distance formula is d equals the square root of x2 minus x1 all squared plus y2 minus y1 all squared. And so to figure that out, I'd have to measure some sides here. So let's do that. So let's find let's measure OP. You know what? Maybe we'll just measure like a couple of these, and then I'll just give you the answers for the rest. Because I'd rather us get to more interesting things than distance formula. And also, I'm afraid I'll do it wrong, and you guys will laugh at me. all over again. All right, here we go. X2 minus X1 all squared plus Y2 minus Y1 all squared is going to equal... All right, like that. -1 all squared is +1. 2 squared is 4. That's going to be the square root of 5, which is approximately, I'm told, 2.2, which is not far enough of an approximation. I'm surprised your book settled for that. Let's find PQ here for our next one. So PQ is going to equal... Oh, thank you. I got the slow clap for doing it right. Excellent. I'm so glad that I can make you proud. 6 minus a -1 squared. All right, you're not proud. Okay. All right, that's fine. My heart was hopeful, I guess. Yeah, you can do better. You're disappointing the Waddy family name. Man, for generations, Waddy math videos will be known. 6 minus a -1 is +7. So we'll square that, plus 3 minus 2 is 1. 1 squared like so. So that's like 49 plus 1. Looks like the square root of 50 to me, which I would break down into the square root of 25 times the square root of 2, because 25 is the largest perfect square that goes into that. Do you guys know how to reduce radicals? I think so. You probably saw that in Algebra 1. Square root of 25 is 5, so 5 rad 2 is the exact distance, but an approximation would be 7.1. All right, so this is like 7.1. This is like 2.2. And then if you did the distance formula over here, you'd get about 6.7. So classification is scalene. I feel like, yeah, if I had a son, I'd name him Vinculum. I've got like 3 sons. Yeah, I had my shot. But I think a daughter named Scalene. No, it sounds like she'd have like a skin disease or something, but like, I don't know. Sounds like that could be a nice name. Yeah. Maybe if she was like part dragon or something. But anyways, how could I determine whether it's a right triangle? Ugh. Measure the angles. How do I know? Let's look at the slope. Down 2 over 1. So here's a slope of -2. And here's a slope of up 2 over 1. Wait a minute. Or sorry, up 1 over 2. My bad. So because the slopes are opposite reciprocals, that is, these lines are perpendicular. And because those lines are perpendicular, then by definition of perpendicular lines, that's a 90-degree angle. It's a right angle. It's a right triangle by definition of right triangle. It's scalene right. All right, so there you go. There you go, friends. Thank you. All right, some names of types of angles in triangles are as shown. Let's scroll down here for a minute. Ooh, wow. Yep, so you've got the interior angles of your triangle, as perhaps you've known. And then did you know that your triangle has, like, armpit angles? That's right. Like, look at those just glowing underarms that this triangle has. It's lovely. I also want to point out that these exterior angles, how do they actually describe them? Angles that form linear pairs with the interior angles are called exterior angles. So notice the exterior angle is not the entire outside angle, okay? That the exterior angles would be like this one and this one. There's actually 2 exterior angles per vertex, but we'll be referring to just one at a time usually, is what we would be saying. And I'm sure, yeah, actually, why are these 2 exterior angles congruent to each other? Oh, well, kind of. You could, because they're both linear pairs to the same one, they're going to be congruent to each other. But they're also vertical angles of each other. But yeah, there is a way you could do it through that. So, oh dear, I just zoomed out a little bit. I had the zoomies. All right. And now that I've defined something, we're going to talk about properties about these exterior and interior angles. And I know you missed them. We're going to do a proof. Everybody's favorite. All right, here is the classic. You guys came into geometry with such confidence. You're like, man, this class is a joke. I already know that the interior angles of a triangle add up to 180 degrees. And you guys probably did know that. But today we're going to prove it to you. It's going to be pretty good. Are you guys ready for this proof? You guys have been told this was true by the system, but you're not a part of this system. You guys, you're taking their theorem and throwing it on the ground because you want proof. Just because something is commonly known doesn't make it a postulate. It still had to be proven. I mean, even the Pythagorean theorem is a theorem, and yeah. So anything that was proven is of theorem or corollary status. Okay, so guys, check this out. Let's do this proof. I actually really like the cleverness of this solution here. So statements and reasons. Like chicken? Yeah, I am. Denver Nuggets? No, not that I know of. Gold? Yes. Wow, I didn't know. He's never told me that. Let's see. So given triangle ABC as such, you could label things like here, you see. And let's start with this. So you've got a triangle. That's your start. Look at this. This is a legal move. Draw BD parallel to AC. It's actually a theorem, and we're trying to prove it right now. No. We got it. Once I prove it, then you can use this triangle sum theorem all the time. Well, this is not part of this line is not part of the original triangle or given information. But do you guys agree that I could draw that for any triangle? All right, using the parallel postulate. I also theoretically could have drawn it over here, right? And I could have had one that was parallel there. So wherever it is, right, you could do that. And then check this out. I'm going to say, this is where we're trying to go, but I'm going to say something about these three angles. What do you think's true here? Yeah, I think I could say that. Measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 is equal to 180. And there's two things that make that true. Angle addition postulate and definition of straight angle. Yeah. All right, so all of these add up to 180, like so. What else do I know? What's something else? I want to try to relate angle 2 to these angles. What's the relationship between angle 4 and angle 1? Alternate interior angles. And by the alternate interior angles theorem, because these lines are already parallel, they will be congruent to each other. Isn't this like a clever setup? Like the fact that they were like, let's make a parallel line so we can use some of our other theorems from days of old. What could I say about angle 5? Yeah, for the same reason. And if those angles are congruent, then their respective measures are equal. Let's see, so I'm going to say measure of angle 4 equals measure of angle 1, and measure of angle 5 equals measure of angle 3. Do you guys remember how to go from congruent to equality? Def of congruent for both of those. Now where's this going? Yeah, we're gonna do some dub sub. Look at that. That is beautiful, friends. Beautiful. So yeah, I think I'm done. I think I can say now that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 by substitution. Isn't that nice? Isn't that like a cool, like, yeah, I believe that's true now, and not just because my middle school teacher told me so. Right? It's lovely. Hmm? Yeah. Yeah, that's a legitimate first step. Yeah, so yeah, absolutely. Right, like if you want to, like, I could have said draw a circle off of B, it got a radius of A. Like, you can do whatever you want, and as long as it's legal, and then use, properties from that, go for it. Go for it. All right, here's another theorem, everyone's favorite, eat. The measure of an exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. So here's my exterior angle. The non-adjacent angles are these two, the ones that it is not touching, and it's equal to the sum of those two angles. And that's one of the things that we had just done here. Look at this. Oh, beautiful, beautiful. Yeah, the two ones right there, they add up to the big one right there. Good. And I think you guys are going to do that proof for homework tonight, if I'm not mistaken. All right, let's do example 3. Let's keep cruising right along here. I'm getting all excited about these proofs. Okay. So, find an angle measure. Okay, so this is an exterior angle. These are the remote interior angles. A relationship I could say about those three things is that 2x minus 5 is equal to x plus 70. And now I could solve like I always did. No. No, I'm not known for my singing, other than that I sing loudly. Waddy sings. Well, I've got my preaching videos, but yeah, I don't sing in my, no. Oh, actually, I did sing in a sermon once, but it was like about a song that we sing to our kids because they keep doing crazy stuff, and then we made a little song for them to remember. Don't do crazy stuff. There you go. True story. I like not professionally. So guys, notice they asked for the measure of JKM, not just the value of X. So that's why I did that last little, right, I just plugged it in. Yeah. All right, let's see. Ooh! Man, guys, this is awesome. This is a big day. This is a really big day for us. Look at, I think I mentioned the word corollary today, but I don't believe I've ever told you what it is. A corollary to a theorem is a statement that can be proved easily using a theorem. Okay? So a corollary is like the classic, right? I made my discoveries by standing on the shoulders of giants. That's the Isaac Newton thing, right? Right. Like a corollary, it's like the theorem did all the work, and then the corollary is just like, oh yeah, you got this little thing right there, and you got that thing too. And then they're like, yeah, but I did all the hard work, and the corollary is like, doesn't matter. I said something that's true. Copyright. Right. So let's see. So the corollary. All right. I'm just gonna stop. I'm just gonna. Here we go. So here's the corollary to the triangle sum theorem. It is a type of theorem. Corollary to the triangle sum theorem. The acute angles of a right triangle are complementary. Huh. Why does it make sense? All right, because we know that this is a 90-degree angle in a right triangle. I know that all three add to 180, right? And then if I subtract 90 from both sides, I'm going to get that these two add to 180 minus 90, which is 90. Yeah, so it's one small step after the right triangle sum theorem. One small step. So let's put that to use. Here, follow along now, gentlemen. All right, in the painting, ooh, abstract art. The red triangle is a right triangle. Right there. The measure of one acute angle in the triangle is twice the measure of another. So they gave me a fact. So like if this is x, then this angle would be 2x. I can't even read that. Find the measure of each angle. What could I do to solve? X plus x equals 90, and that's true because of the corollary of the triangle sum theorem. So that's 3x equals 90, and then x equals 30. And they wanted to find the measure of each acute angle. Well, one of them was just x, so that one's 30 degrees. And then the other one is 2x, which is going to be 60 degrees. There you go. Oh, and that's the classic 30, 60, 90 right triangle. Oh, tell you what, we will one day discover all sorts of things related to that. Well, thank you for watching, Internet friends, and have a great day.